So happy Friday, everybody. My name is Bob Laramie from Swansea University, Department of Computer Science. Thank you, Matt, and the organizers for inviting me here to speak today. So Matt thought it would be a good idea just to show something that we work on inside of the department in a little bit more depth, and some activity that will also take place in the computational foundry. And it also is related to the event here, but it's essentially the visualization of healthcare data, aptly titled Bringing Healthcare Data to Life Through Visualization. But before I start talking about that, I have some advertising to do. So this is for another event. So the department is hosting a conference in September called the Computer Graphics and Visual Computing Conference. It will be on the 13th and 14th of September. And there will be lots of very talented people there in visual computing, so data visualization, vision, computer graphics. So if you're looking to speak to talented people in that, specialists in that field, it might be a very interesting event for you, especially if you're trying to recruit talent. So we're happy to have as many people there as possible, especially industry presence or anybody that's looking to recruit talent. And actually, the School of Medicine at Swansea University does recruit these people, and they work there now. So it all fits together somehow. And I'm one of the organizers, so if you have any questions about that event, please just let me know. Another advertisement. The College of Science at Swansea University has a new-ish match funding scheme for PhD students. So if you or your organization is interested in having a full-time PhD student that's doing research just for you and your institute, you can let us know. And so the idea is that the College of Science pays for half of the student fees, and the industry partner pays for the other half of the bursary and the stipend. So it's a 50-50 split. And why is that interesting? So if you're a business or maybe a researcher, you depend on innovation, right, to remain competitive. And this is what we do. This is our job. We sit around and we try to think of innovative methods that solve problems. That's all we do. I mean, well, that's not the only thing we do, but that's what we're here for. That is our job. And we know that innovation and this kind of expertise can give any industry a competitive edge. It's very cheap labor compared to actually hiring somebody in your department or your institute, right? It's only $11K per year over 3 years, which is a lot cheaper than actually hiring somebody in terms of an actual fixed employee. You get two for the price of one, so you're actually hiring two people. You're hiring a PhD candidate and their supervisor. They work very closely together to develop innovative solutions to whatever problems you're working on. You get tax deductions for research, right? And you can test out a prospective employee. It's always nice to be able to test out a prospective employee before you hire them on. If you have any questions about that, please let me know as well. We currently have 3-ish PhD candidates in data visualization, all supported by industry. And Matt Roach actually highlighted one of them, which was the visualization of call center data. So the QPC is the partner in that case, and they really want a competitive advantage over their other industry partners, and gaining insight into call center data to improve their operational efficiency. So on to the main business, which is the healthcare, bringing healthcare data to life with data visualization. So in case you haven't noticed, that's one of the areas we specialize in the department. Anybody here looking at healthcare data? Is there anybody here studying that? Yep. I noticed there are lots of people at this event since it has something to do with the School of Medicine at Swansea University. Right, everybody that's looking at this knows what a challenge it is, right? It's a very difficult challenge, right? And these are some of the challenges that are highlighted in an infographic, right? The data is very chaotic. It comes from lots of different sources, and trying to bring it together in a cohesive way is very challenging. There's the word location here, and we're going to use it in a different sense than what's depicted in this infographic. What we're going to look at is trying to couple that complex, high-dimensional healthcare data with geospace onto a map to make sense out of it. Is this possible, and how can this be done? And there are other challenges, like trying to figure out what your data is, trying to understand all the different data formats, and the sheer complexity of the data. There's one problem that's implicit here that's not mentioned, and that is the data set sizes. They can be really, really big, right? And this is the strength of data visualization, giving you understanding of very large data sets. That's one of the main advantages of this, that this field has to offer. Other nice things that visualization as a field has to offer is the ability to explore data. So if you want to gain an understanding and you don't even know what the data looks like, you didn't create it yourself, you want to know just what it looks like and what its characteristics are, if there are patterns, outliers, that's it. That's exploration. It's good for analysis. That's after your exploration phase. If you have formulated a hypothesis and you want to confirm or refute a hypothesis, you can use data visualization for that. We usually associate it with presentations, so showing nice images of your exploration and analysis to and communicating it to a wider audience is what we're going to do today. It's also very good at acceleration. So when you're looking for something, you can perform a search, a visual search, very quickly using imagery rather than actually looking at numbers, trying to search through raw numbers, or trying to use a text-based search engine. You can find patterns or something you're looking for very quickly when it's shown in an image. It's also good for increasing confidence. Some people in the world of healthcare call this validation. So if you want to validate what a hypothesis or if what you're doing is correct or incorrect, data visualization is very useful for this. And this happens all the time. So before we talk about the innovation, I was going to give a little bit of background. And actually, some of you might get a little bit nervous now, because I'm going to ask you some questions. Audience questions, and see if you're awake. Has anybody here heard of Treemaps before? 1, 2, 3, 4. Oh, that's good. 5. Okay, that's good. So those 5 people will know what this is. For the rest of the people, I'm going to try to explain what a tree map is in just 30 seconds. So a very common source of data is hierarchical data, right? And the question is, how do you visualize large hierarchies of data? This is a very small hierarchy, right? With 1, 2, 3, around a dozen data samples. What if you have 1 million data samples in that hierarchy? You cannot just draw a hierarchy on the screen anymore and visualize the data. It's just not possible, right? There's not enough screen space. But there is another way, and it's called a tree map. So this is an example of a tree map, and it fills the screen space with rectangles and distributes the data across the screen space. So these two are actually equivalent to each other. And how do we interpret that? So each node in this hierarchy is assigned a rectangle in that space, right? This is the root node of the hierarchy, and this occupies the top level rectangle, so the whole screen space. So the root node of the hierarchy gets the whole screen, so to speak, and then it's subdivided by its children. So in this case, we have 1, 2, 3, 4 children, right? And there are 4 rectangles that represent these 4 children. The 12 is a leaf node, and it gets this rectangle right here. It's mapped to this rectangle. The 8 is a leaf node, right? So it gets this rectangle here. This is not a leaf node, it's an internal node. And it gets its own rectangle that's right here. Right? And it's subdivided recursively again into 1, 2, 3, 4, 5 rectangles. These 5 rectangles. Which leaves us with one more internal node, and that node is mapped to this larger rectangle, and it's subdivided 2 more times. So there's a rectangle here containing 6, 8, and 11. Right there. There's a 5, there's the 5, it's a long rectangle, and then there's a 40, which is a leaf node, which is the big rectangle. So the rectangle's size is proportional to the amount of data that they represent. Right, that 40 is a big rectangle. Now how that layout process actually functions, we're not going to get into detail about how that works, because it's complicated, and there are 20 different ways that you can try to lay out this data in a tree map. But that's the idea. Did I lose everybody on that? Everybody knows what a tree map is now? This is another example. And yeah, this is very, very similar. I just show this because in the previous example you couldn't see any borders between the parents and the child nodes, but now you can see explicit padding. So you can see the root node explicitly, and it's got some padding before the first child node is placed, right? And then you can see C30 here, and then you can see D62. It's not a very high quality image, but D62 is subdivided, and you can see that more explicitly because there's some padding added. Those images are a little bit old. I think they are from 1991. So I'll show you a modern version. Has anybody ever wondered where did all your disk space go? You're using a laptop or a desktop and you run out of disk space, or your disk space is getting short, and you're just like, where did it all go? I don't understand how this is possible. This can't be possible. So this is a modern kind of example of a tree map. This is a tree map of a disk. In this case, it's this disk. So your disk is a very common source of hierarchical data. It has a root folder, and inside there are more folders, and inside of those there are more folders. So all the folders get mapped to a rectangle, and all the files get mapped to leaf node rectangles in this tree map. Right? And I can see like where my disk space is being occupied. So if I'm trying to free up disk space, I may as well go for the big files. I use this program all the time, by the way, all the time, because I'm always running out of space. This is a free program. It's called Disk Inventory X. Anybody can download it and use it. Right? Anybody. So it's free, and there's an equivalent version for the PC. But look. Now I can move the mouse over the rectangles and I find out what those files are. I find out the path of the file and the name of the file, right? And what they are. So this is a lot of audio files because I listen to a lot of audio books, right? This is the biggest file on the computer by far, and it's where it's where the iMovie stores the movies. So that's just a little example of an actual tree map in action. And tree maps have some nice properties. They're space filling, they're hierarchical, they can we can depict multivariate data, and they apply to large data sets, but there's no geospace in there. Right? If I want to look at healthcare data on a map of the UK, I can't do that with the tree map very well. However, I can use something called a cartogram. Anybody heard of a cartogram before? Good, good. So this is a traditional geospatial map looking at one variant. So you take a variant, you map it to color, and then you depict every area with that color. Look at what happens though in London. Wherever there are densely populated areas, the data gets compacted and it's no longer perceivable. So one way to alleviate that is with cartograms. Cartograms take each shape and assign it to some fixed ellipse, for example, and then the radius of the ellipse changes depending on the data that is mapped to. Right? So look what happens for this. This is the cartogram in London gets expanded. So the data inside London gets expanded. Cartograms are great, right? They include geospatial information. They're very engaging, right? When everybody sees a map or a cartogram, they suddenly wake up. It's very engaging. People love maps and cartograms, including myself. They also increase memorability, right? If I tested you using some map, you perform better. They're not necessarily space efficient. They're univariate typically, meaning they can only represent one variable at a time. They introduce geospatial data and they're generally flat, so not hierarchical. And the question is, can we combine properties of cartograms and tree maps together and get the benefits of both? And that's part of the innovation now that we're working on here at Swansea University. So we are working on something called the Cartographic Tree Map. Right? And here's a picture of an image of the Cartographic Tree Map. It includes geospatial information. It's space efficient, so it spreads the data across the screen space. It supports multivariate data, hierarchical data, and it's also engaging. And we're going to give a 60-second demo of that before we run out of time, of what that looks like in action, so to speak, when you actually use the software. So this is the software in action, so to speak. I should probably hit the play button. And this is in conjunction with the School of Medicine at Swansea University. Right? This is the layout algorithm. So these are CCGs, the clinical commissioning groups. There are 209 of them across England. Each one of those rectangles represents a clinical commissioning group and the services and the diagnosis that occur inside the clinical commissioning groups. This is the layout algorithm of those CCGs, so taking place interactively in an animated way so we can see how it's working and what's happening. Right? And if we pause it, or if we look inside each CCG, we can see a number of rectangles, smaller rectangles. Right? And each one of those is mapped to a diagnosis that we see along the color legend. Coronary heart disease, heart failure, stroke, chronic kidney disease, diabetes, hypertension, and so on. So in this particular example, we chose 14 variants. And we can see right away, for example, hypertension and diabetes are the two most prevalent diagnoses across England. You can see that in seconds with these cartographic tree maps, right? Without even, without looking very carefully. That's what they look like when we adjust the size of the CCG based on population, for example, the local population. And this is what it looks like if we group CCGs together into higher level into higher level abstractions, it starts to look more and more like a traditional tree map. Right? And we also have the ability to click on an individual CCG and get an exploded view of that, and then use the mouse to gather the original, or look at the original data that it represents, the original quantities, the number of diagnoses. Okay, I think the time is basically up. Are there any questions or comments about that? If you're interested in this, we are still working on it, and we're also working on a bid for the visualization of healthcare data that we're putting together for EPSRC. If you're interested in that, please let me know. Thank you very much.
Thank you very much. I found that absolutely fascinating. And sort of just looking at the nods, the head to the back of the piece. Yeah. Introduce you to Treemaps Example. Development of this service. So dementia is, I've forgotten what I was going to say about this. So dementia is one of the biggest global health and social care challenges that we face. And with a growing percentage of the population developing this disease, the Dementias Platform UK, or DPUK, was founded. And